Yeah, good morning, friends. So, in the last class, we are discussing principle of proton NMR spectroscopy. We discussed their quantum approach. Here, generally, quantum approach deals with fixed energy levels and nuclear magnets transition between lower energy level and higher energy level under the influence of applied magnetic field, and it receives some energy from external energy source, that is RF energy source. So substantially the magnet will transit from lower energy level to upper energy level. It absorbs some RF energy, and when it relaxes means it bounces back to higher energy level to lower energy level. It emits some energy. So there, uh, that energy absorbed or energy emitted is uh, understood by or read by the computer, and we will get signal of proton NMR according to quantum approach. And here, classical approach or Newtonian approach. So this classical approach is not bother about the energy levels. It is not bother about energy level. So in the classical approach here, here the nuclear magnet takes precision. Precision, it is, you can define precision as a spinning body rotating about its axis with some tip angle. Tip angle is called as precision movement. పురస్సరణ చలనం. ఏదైనా భ్రమణంలో ఉన్నటువంటి పదార్థము దాని యొక్క అక్షం పరంగా చలిస్తూ ఉంటే, కొంత కోణంతో చలిస్తూ ఉంటే దాన్ని పురస్సరణ చలనము అంటారు. రైట్. సో లెట్ us suppose this is the spinning body, and here this spinning body under the influence of external force or external magnetic field. So here this body is moving like this, right? So with an angle of theta with respect to its axis, this angle is called as tip angle, right? Right. And here this, the direction of this magnet is aligned with the external magnetic field, aligned with the external magnetic field, right? And when you give or when you supply some RF energy, okay, so here this spinning top or this nuclear magnet will flip and converted into higher energy precessing body. And here the direction of this will change, and it is with opposed direction with respect to external magnetic field, right? So here, when you apply some external magnetic field, this nuclear magnet, okay, so it goes on precessing, right, with some tip angle theta, and here the direction of this precision is aligned with external magnetic field. And when you give some external energy, RF energy, so the energy increases and this will flip and rotates in opposite direction, and it is high energetic precision now, right? And this is low energetic precision, right? So here number of rotations per second is called as precessional frequency. Number of rotations around axis is called as precessional frequency, right? Per second. And since nuclear magnet has high precessional frequency, that is in the ranges of 10 to the power of 6 precisions per second, so we generally write it as 10 to the power of 6 megahertz range, right? So this precision is also called as Larmor precessional frequency, Larmor precessional frequency, right? So it is the precessing body, right, under the influence of external magnetic field, right? So at resonance conditions, right, here also resonance is equal to matching of frequencies when the frequency of applied radio source energy is equal to the precessional frequency of the nuclear magnet. So this nuclear magnet then at resonance conditions receives radio energy, and it starts spinning, or it will flip, okay, it will flip and flip to the higher energetic precision. So now it will rotates in opposite direction. So in the quantum approach and in the classical approach, in both the cases resonance is the condition, and here the computer will take the energy absorbed by this spinning top or magnet, right, to flip from aligned level to opposite level, right, and eventually this absorbed energy is read by computer or NMR meter, and you will get graph accordingly like this, right. So here there are few factors which influence hence precessional frequency or Larmor frequency. So higher the applied external magnetic field, higher will be the precessional frequency. So this is strength of applied magnetic field. And here there is another one, gyromagnetic ratio, magnetic ratio of the spinning body. And in the case of proton NMR, it is the gyromagnetic ratio of a proton, that is around 26,653 gas rotations per gas and per second, right. And here third one, magnetic moment of the nucleus, whether that nucleus is magnetically active or inactive, right. If it is more active or if it has more magnetic moment, it will have higher precessional frequency like that. And there are certain factors which will also influence the precessional frequency. So nucleus is influenced by the surrounded electrons. So electron density around nucleus, so since these electrons are also charged bodies, they are spinning bodies. So according to Joule's rule, right, any spinning charged body, right, can generate its own magnetic field. So here the magnetic field generated by these electrons nearer to the nucleus influences the magnetic nature of the nucleus. So this also influences the Larmor frequency of the nucleus, right. And here nature of the nucleus, okay, nature of the nucleus. So nature of the nucleus, and so there are certain factors which will influence the nucleus, right. So these are the factors which will influence the Larmor frequency or precessional frequency: strength of the external magnetic field, gyromagnetic ratio, right, and a magnetic moment of the nucleus, and electron density around the nucleus, nature of the nucleus. So as we already discussed, this frequency or precessional frequency is always in proportions to the strength of external magnetic field applied, and we know frequency is equal to H dot gamma gyromagnetic ratio upon 2 pi, right. So we already knew this formula in the quantum approach, also we applied. And so at any given field, strength, Larmor frequency is equal to H dot H naught. H naught means this is applied magnetic field, and gamma gyromagnetic ratio upon 2 pi. And so here gamma L is also directly proportional to Larmor frequency is directly proportional to gamma, and it is also, as I said, is directly proportional to the magnetic moment of the nucleus. All right.